Implicit differentiation. Suppose you wanted to determine the slope of a circle. Now we'll have a circle with center at the origin 0, 0, radius of 1, and we want to know the slope at any point along the circle. The equation of the circle is x squared plus y squared is 1. Let's look at the circle. We can easily visualize it. And we can even visualize what the slope would be at certain key points, say at 1, 0, say at 0, 1. And maybe we can even infer what the slope may be along the line y equals x, where it would intersect the circle. But we need to be cautious. There are two functions that are needed to graph a circle. The top half of the circle is graphed by y equals the square root of 1 minus x squared, while the bottom half of the circle is graphed from a different function, y equals negative square root of 1 minus x squared. Which equation would you choose? Well, depending upon what point on the circle you want to know the slope of that circle for, you would have to pick the appropriate function and differentiate. Up until now, the functions that we have encountered can be described by expressing one variable explicitly in terms of another variable. But many curves have equations that cannot be expressed explicitly. Certainly the circle that we looked at, ellipses, hyperbolas are examples of curves whose equations are such where it would be difficult to express in terms of one variable solved in terms of the other. Here are a few other examples. X squared plus y squared is 2y. You see the associated graph of this curve. It's not a function, but we can still attempt to find the slope for any point along the curve. And that's really our goal. E to the xy equals 5y. Again, here is the curve for this particular equation. Again, not a function, but we may find the slope for any point along this curve. And a third example, x ln of y plus y equals 3. Again, not a function. It is difficult to impossible at times to solve for one variable in terms of the other. So what our goal is, we want to determine dy dx, and we will use implicit differentiation. Implicit differentiation consists of two steps. The first is to differentiate both sides of the equation with respect to x. When performing the differentiation, remember y is a function of x. If you think of the circle, you know specifically what function of x is for y. Y is either the square root of 1 minus x squared or negative the square root of 1 minus x squared. So this means that we'll have to use the chain rule on each variable y term, since y is a function of x. The second step is to then solve for dy dx, treat it as a variable, and isolate it. Let us return to our circle centered at the origin radius 1. We will differentiate x squared and get 2x. We will differentiate y squared and get 2y, but because y is a function of x, it is multiplied the chain rule times dy dx. You see it highlighted in blue. The derivative of 1 is 0. Now our goal is to isolate dy dx, solve for it. So we'll subtract 2x to move it to the right side, and then divide by 2y. Now we can simplify, and we find dy dx is negative x divided by y. This is the formula that we were in quest of in the first slide. This will enable us to find the slope for any point along the circle. So let's look at 1, 0. Plug in x is 1 and y is 0 into our equation. And we find that the slope will be that of a vertical line. The slope itself is undefined. The tangent line will be a vertical line. Let's look at dy dx and evaluate it at 0, 1. Plug in x is 0, y is 1, and we find the slope of the curve at 0, 1 to be 0. The visual we have is that of a horizontal line at that point. And lastly, we'll take a look at finding the slope along the line y equals x. And we'll look at negative 1 over the square root of 2, comma, negative 1 over the square root of 2. Our slope is a negative, these two negatives would cross out, negative 1. Let's put a visual onto this particular problem. Here is our circle. Here is our point 1, 0. Slope of the vertical line is undefined. Here is the point 0, 1. Slope of the horizontal line is 0. And here is the third point. Slope of that line, negative 1. Let's look at a second curve. X squared plus y cubed equals 2y. We can see the graph of this particular equation off in the corner. First thing we do, we write down the equation, and then we use the chain rule to differentiate. Any term that has a y, we use or apply the chain rule. Differentiate x squared, we get 2x. Differentiate y cubed, we get 3y squared, chain rule, times dy dx. Differentiate 2y, and we get 2. But again, since y is a function of x, times dy dx. What do we do next? Well, we want to isolate dy dx, so we will move dy dx so all the terms are on one side of the equation. Any terms without dy dx are on the other side of the equation. So, if you take a look, we subtracted the 2x term and subtracted the 2 times dy dx term so that we can group the dy dx's on the left side of the equation. What would we do next? Well, again, our goal is to isolate dy dx, solve for it. We see it appearing in each term, so we factor out dy dx. That would leave dy dx times 3y squared minus 2, quantity, equal negative 2x. Our last step is to simply divide both sides of the equation by the same term, the multiplier to the dy dx, 3y squared minus 2. And we have a formula that will give the slope for any point along our curve, which is shown in the right corner. The formula would be negative 2x divided by 3y squared minus 2. Let's look at another curve whose graph is in the corner. The reason why we want to explore this particular equation is because you will see a chain rule, and within the chain rule you should see a product rule. And within the product rule you should see a chain rule. Now, let's take a look and see what we're talking about here. Write down the equation. First step, use the chain rule, but in this case our chain rule includes the product rule. This is because the left side of the equation is in the form of e to the u. The derivative is e to the u times u prime. What's u? U is x times y. To determine u prime, we use the product rule. We take x times the derivative of y, again the chain rule, plus the derivative of x, which is 1, times y. Substituting in, we have e to the u times u prime, and we replace u with xy. We have e to the xy. We replace u prime with x dy dx plus y. And we set that equal to the derivative of 5y. Well, again, the chain rule, that's 5 times 1 times dy dx. Our goal is to isolate dy dx, but notice dy dx is in the parentheses on the left side of the equation, not in the parentheses on the right side of the equation. So, before we can proceed to group the terms, let us distribute e to the xy through the parentheses so that we can see the terms added or subtracted without being embedded in parentheses. We have x e to the xy times dy dx plus y times e to the xy. On the right side of the equation, we still have 5 dy dx. Again, we want to isolate dy dx. So again, we're thinking any term without dy dx will move to, in this case, the right side, and any term with dy dx will move to, in this case, the left side. So let's bring the terms that have dy dx to one side of the equation. Subtract over 5 dx dy, subtract over our y e to the xy. What's our next step? Well, we notice these two terms both have a common factor of dy dx. So let us factor out the common factor. And to finish the process, we will divide both sides by the same term, isolating dy dx. So the equation to find the slope for any point along this curve is negative y e to the xy divided by x e to the xy minus 5. Notice a small but important point. To find the slope of the curve at any point, you need both x and y. So that for one value of x, the particular value of y will talk about the slope at that location. Let's take a look at x natural log of y plus y equals 3, whose graph of this curve, this curve's equation, is in the right corner. Write down the equation, and in red you see x natural log of y. So if you're differentiating, you're thinking to yourself, I see a product, I will use the product rule. So the product rule, to remind you, f times g, its derivative is f prime g plus fg prime. For us, we'll call fx and g natural log of y. Substituting in x ln of y, the derivative of x is 1, times the natural log of y, plus x times the derivative of the natural log of y. Well, that's 1 over y, but again, y is assumed to be a function of x. So times dy dx, the chain rule, is sitting in this step that I'm underlining. Next, we want to differentiate y. The derivative of y, dy dx, 1 times dy dx, and the derivative of 3 is 0. We need to bring the terms with dy dx to one side of the equation and move the terms that don't have dy dx to the other side. So we will subtract over any term without dy dx to the right side. As we did in the previous two examples, we noticed that both terms have a dy dx. What do? Factor out the common factor. Dy dx times the quantity x over y plus 1 equals minus the natural log of y. Now, we are one step away from finishing. If we simply divide both sides but the quantity in the parentheses, we would be done. But this would create a complex fraction. So instead, we'll take a second to simplify. We'll find a common denominator, rewriting 1 as y over y, and forming a common denominator, so x over y plus y over y is x plus y over y. That way, when we proceed to isolate dy dx, we will invert and multiply, and we end up with minus y natural log of y divided by x plus y. Thank you.